Hi everyone, welcome to this talk. My name is Rituraj Singh and I'm a software engineer in the AI training team at Bloomberg. And I'm going to talk about ensuring reliability in Bloomberg's cloud-native Jupyter Notebook platform. So let's get right into it. So in this talk, I'll start with an overview of the AI infrastructure at Bloomberg. We'll begin with a quick look at some of the key Kubernetes concepts, some building blocks, which is the backbone of our AI platform. Then, I'll walk through the Jupyter Notebook platform that our ML engineers use and explain how we ensure reliability through a framework built on Argo Workflows and Jupyter API. And finally, we'll explore some reliability measures and how we define service-level objectives and service-level agreements that gives us a clear insight into the health of the platform. So the backbone of AI at Bloomberg is its data science platform. It's a unified infrastructure for all things machine learning, large-scale computation, and data science. It's a multi-cluster, multi-tenant system built on top of Kubernetes and is designed to support workloads across teams and regions. Now, the platform provides a complete MLOps experience. So we have data gathering and data exploration with Jupyter Notebooks. We have model development, training, deployment of inference services, and more. And all of this is powered by state-of-the-art compute and GPUs. Now, under the hood, it brings together a rich ecosystem of open source technologies. So we have Jupyter for data science. We have Kubeflow and Ray for model training. There's Kserve for inference, and Karmada for multi-cluster orchestration, among many others. Now today, we are going to focus on one part of this platform, which is the Jupyter Notebook. So let's look at this image. Now, this is showing Jupyter Notebooks as a service at Bloomberg. And let me unpack each of these layers. So at the base of it, we have CPU and GPU nodes, which are the actual machines providing the compute power for all workloads. Now, whether that's lightweight data exploration or something heavy like training on GPUs, it supports that. And on top of that, we have Kubernetes. Now, this handles scheduling, resource management, and container orchestration. So it's the foundation that allows us to run notebooks in a consistent and declarative way. So above that, we have some core platform services that handle networking and security. And all of these are like open source projects. So Istio is for service mesh and traffic management. We have Calico for network policy enforcement. We have OPA, or Open Policy Agent, for access control and governance. We also have some device plugins which we use to expose GPUs. And we have a secret store CSI driver for securing secrets and credential management. And the next layer focuses on observability and metadata. So we collect logs, events, metrics for every notebook and every service that we launch. And on top of that, we have some identity controllers, which we use to integrate with Bloomberg's authentication systems. And this ensures that each notebook maps to the right user who has the right permissions. And finally, at the very top, we have the Jupyter Notebook controller, which encapsulates all of this together. So it watches for notebook creation requests, provisions the necessary resources, and manages the full lifecycle of notebook instances. So let's talk a bit about Kubernetes. Now, Kubernetes is an open source platform. It automates how we deploy, scale, and manage containerized applications. And in simpler terms, it acts as the control plane for distributed workloads. Now, in the context of machine learning, Kubernetes ensures that workloads like model training jobs and Jupyter Notebooks run seamlessly. It also provides some strong tenant isolation. So we need this because we don't want teams competing for the same resources on a cluster. So this makes it ideal for shared ML platforms and research environments. So let us look at some basic building blocks of Kubernetes, and that is going to help us understand the validation framework that we use with Jupyter API and Argo Workflows. Okay, so this is a node. Now you can think of a node as your server in the cluster that hosts multiple workloads. It provides with compute, memory, and networking resources. Now a pod is the smallest deployable unit in Kubernetes. It's a logical wrapper around one or more containers that share the same network and the same storage. So it's important to remember that these pods are ephemeral, but Kubernetes is smart enough to launch this pod again if it dies. And that helps us in making sure that the application is always up and running. Containers. So containers are where your actual code runs. It's going to package everything from your code, your dependencies, and your configuration into an isolated environment. Now, Kubernetes doesn't manage containers directly, but it uses pods for that. So pods group containers together in a logical way, and Kubernetes manages these pods. Now let's look at a service. So in Kubernetes, a service acts as a virtual load balancer. So in this case, you can see there's a user who is trying to ping the URL myservice.com. The request goes through a Kubernetes service, which is backed by a certain pod, one of the healthy pods. The pod is going to process that request and send it back to the user through the same path. Now, this allows applications to communicate reliably, even as pods are recreated under the hood or rescheduled across nodes. And finally, this is your Kubernetes cluster with multiple nodes and each node running multiple pods and each pod running multiple containers, which actually hosts your application. So let's look at Jupyter Notebook on Kubernetes and how it works for an actual user. So in this case, you can see that there's a user who's trying to submit a request for a Jupyter Notebook resource. You can see that at the very top, we have the kind Jupyter Notebook, which is a resource that we are going to submit on Kubernetes. There's a name and a namespace, and there's a specification that has some details. The image is Jupyter Lab, because we want to run a Jupyter Lab instance, and maybe you want to connect to some remote storage to fetch some data. So let's say you have an S3 identity, so we have mentioned that as well. And maybe you need to initialize a GitHub repository when your notebook starts. So you can mention a Git URL as well. You might be needing some packages that you want to use for training a model or exploring some data science tasks. So you have to install some pip packages. So in this case, we have torch and transformers. And finally, each notebook instance or Jupyter Lab instance needs some compute resources. So in this case, we are using 2 CPUs, 1 GPUs, and some memory. So in this case, we have 64 gigs. So what's going to happen is that the user is going to submit this YAML to the Kubernetes cluster. And on our notebook cluster, we have something called as a Jupyter Notebook controller. Now, the responsibility of this controller is to parse this YAML and provision the resources required from the YAML. It understands all of the requirements that the user is trying to get. Whoops. Yeah. And so the controller launches a pod on the cluster with the requirements that the user has provided. So we have 1 CPU, 2 GPUs, and some memory. I might have switched the CPU and GPU. And so we have a container which is running the Jupyter Lab image inside of this pod. And then the Jupyter Notebook controller is going to create a Kubernetes service, which would look something like this. And behind this is the pod that we just launched. Now the user can access this URL, and they can open up their Jupyter Lab instance and start working with their notebooks, create code, execute code, and whatnot. Now, in case you missed it earlier, there was a great talk by my colleagues Tucker and Yifan on securing and scaling Jupyter at Bloomberg, a Kubernetes-native approach. So I would encourage you to take a look at that and understand all of the authentication and authorization mechanism that goes behind the scenes once the recording is available. Okay, so when users launch notebooks, they see a simple interface. They see a cell, they create new notebooks, they execute some code. But behind that, there's a complex ecosystem that has to evolve constantly. And that has to happen without breaking the user experience. So this slide shows some points. So we have compute upgrades, we have Kubernetes upgrades, we have some Jupyter upgrades, because Jupyter itself has releases very frequently. We also need to make sure that we have connectivity to GPUs, and there are multiple dependencies that we need to manage. There are features like Jupyter AI, which are upcoming, and that requires connectivity to LLM endpoints as well, and other internal services and ML tools. So behind every notebook, there's a coordinated system of compute, Kubernetes, Jupyter, GPUs, multiple dependencies. And all of this has to work together to make the experience feel effortless for the user. But the real challenge and our success is in making that complexity invisible to the user. Okay, so when we think about features in a platform, we often think of functionality, right? So we need to see whether users can launch notebooks and how they interact with it. But for infrastructure platforms, reliability itself is a feature. Now, if the system isn't reliable, or if your notebooks fail to launch, that is not going to give a good experience to the users. So we measure reliability across several dimensions, and these are some of them. So in terms of user experience monitoring, we check whether users can launch notebooks successfully. And if they can launch notebooks, how fast are those notebooks launching? And even if those notebooks are launching, are those even accessible? And that means, is the authorization and authentication system even working? In terms of platform health, we need to make sure that connectivity to ML tools and services is established at all times. And maybe you created a new cluster with a new set of compute nodes, maybe some new GPUs. how do you validate whether this cluster is ready to onboard new workloads or new Jupyter notebooks for users without disrupting anyone's workflow? And to encapsulate all of this, do you have the right metrics and log traces and meaningful alerts? And do you have the right SLAs and SLOs defined that are met consistently? So there's one way to do it. Simply launch a notebook on the cluster, see if it's working, run some notebooks, and execute some code, and call it a day. But that is not very scalable. You need something which is automated and schedulable, and most importantly, it should be reproducible. So with that, let me introduce to something called Argo Workflows. Now, Argo is an open source container native project for orchestrating parallel jobs on Kubernetes. You can define a workflow as a directed acyclic graph, where each step is a pod in itself. And you can also configure scheduling. So basically, in this workflow, you can ask it to schedule at a certain time on a certain day, and even change the frequency. The nice thing about Argo is that you can use Jupyter Notebook jobs, and you can launch them automatically using Argo Workflows. And there's one more caveat to it. If you have certain dependencies, like if you have step A and step B, and they are dependent on each other, if one of them fails, it's going to fail the workflow. And that is something that we desire. So let us look at a workflow example. So at the very top, you can see that the kind is a workflow, which is a resource that we're going to submit on the cluster. In the specification, we have an entry point called pipeline. And in this case, we have a directed acyclic graph with 2 steps. The first step is to run a notebook, and the second step is to run a tester pod. So let's take a look at what's happening in these 2 steps. So in the first step, we are asking the Argo instance to launch a Jupyter Notebook job. And it does that by running this command that you see in the second box. It runs kubectl create -f, some notebook specification YAML, and it submits it to the cluster. And this is going to create a notebook instance or a Jupyter Lab instance on the cluster. In the next step, we launch something called as a tester pod. Now this pod should act like a real user. The goal of this tester pod is to interact with the Jupyter Notebook just like a user would. So creating notebooks, executing code, creating kernels, and evaluating results. So the question is, how does the tester pod actually interact with the Jupyter Notebook? So let's see. But to understand that, we first need to understand what a Jupyter server is. So Jupyter Server provides core services, APIs, and REST endpoints that connect 3 components of the Jupyter system: the browser, the kernel, and the file system. And the communication happens over HTTP, WebSockets, and 0MQ. Now, the responsibility of this Jupyter server is to create or delete notebooks, launch and manage kernels, and route code cells to the kernel, which is going to execute the code and return the output back to the server, which is eventually shown to the user on the UI. It also does file management and credential management. And the nice thing about Jupyter is that all of these functionalities on Jupyter Server are exposed as an API. Now, if you have a user who has access to a certain URL for a Jupyter Lab instance, so it looks like jupyternotebook.kubernetescluster.com, they can actually ping the endpoints for Jupyter API, such as getting content. So you can get contents out of the notebook. You can post content. So you can also create new notebooks or create new kernels. You can also establish a WebSocket for a certain kernel ID to execute code. So do take a look at the REST API documentation that Jupyter provides. Okay, so now let's look at some pseudocode. So inside of this tester pod, we have a script that looks something like this. Now we have a few functions here. We have a function for creating a notebook, creating a kernel, killing a kernel, and executing notebook code. And if you see, each of these functions is going to call the Jupyter API. So some of these call the get endpoint, some of these call the post endpoint to create content and kernels. So let's see it in action. But before we do that, let me just give you a quick recap of the Argo workflow. So the first step was to launch a Jupyter Notebook job on the Kubernetes cluster, and that's going to create a pod that has your Jupyter Lab. And the second step is to launch a tester pod. Inside of this tester pod, we have a container which is running. So there are 3 components. The first is the list of test notebooks that you need to validate. So these notebooks might be checking whether you have access to GPUs, whether you have access to S3, or are libraries like PyTorch or transformers even working. The second is a script that we just saw, and that's going to interact with the Jupyter API. Sorry. And the third is the expected assertions file. So in this case, once the notebook is executed, we'll have some output, and we need to validate whether the output is expected or not. And that's what we use this file for. So let's see it in action. Okay, so the first step is creating a notebook. And in this case, we call the post endpoint of the Jupyter API by taking the notebook in the container image of the tester pod and sending it to the notebook pod, which has the Jupyter Lab instance. And this is going to create a new notebook in that pod. Next, we create a kernel. We do need a kernel to execute code. So for that, we call the post endpoint for creating a kernel, and we get a kernel ID in return. And then we establish a WebSocket to this notebook kernel and start executing code that was there in the notebook. Now, we will get some output from the notebook, and we do need to validate it. So we call the get endpoint of the Jupyter API, fetch all of the contents of the notebook, and match it with the expected assertions. If there's a match, that means your notebook has passed. But if not, then we use the Slack API to ping the on-call contact for further investigation. And that's where we need to investigate what's wrong with the system. So the question is, what are we actually checking in these notebooks? Now, this is not an exhaustive list, but these are some of the things that we actually check. We check whether notebooks can be launched and are even accessible, whether code can be executed, whether we have GPU connectivity, or do we have access to models and dataset registry. We also test some Jupyter features like Jupyter AI, and whether ML libraries are accessible like PyTorch, Hugging Face, transformers, and of course, LLM endpoints. So to summarize this part, you can launch Jupyter Notebook jobs using Argo Workflows on your Kubernetes cluster. And you can spawn tester pods in parallel that use the Jupyter API to create, execute, and validate notebooks. And you can automate this workflow by defining a cron schedule and base it on some frequency, like every day or every hour. Now, why does this even matter? Why does automated notebook validation matter to us? So automated notebook validation has become a core component of how we maintain reliability. It gives us confidence before deployments and helps us in detecting breakages quite early. We don't want to push out a feature on the platform and break our users' workflow. So it confirms compatibility as our infrastructure evolves. Now, most importantly, it saves a huge amount of engineering effort by replacing repetitive manual checks with automated consistent validation that we use by integrating Argo Workflows with Jupyter API. Okay, so we do have a validation framework in place, but how do we actually measure the platform's health every day and every hour? And for that, we define some SLOs and SLAs, so service level objectives and service level agreements. And here are two examples of how we do it. So the first one is the notebook pod initialization time. In this case, the pod initialization should complete within n seconds for at least 99% of the launches. Now, what that means is that when our pod gets launched on the Kubernetes cluster, it's going to do a few steps. It's going to fetch the image for the notebook. It's going to get some identities, maybe some secrets, or initialize some GitHub repositories. And all of this takes a bit of time. So if your SLO is defined as, let's say, 30 seconds, that means all of your notebooks, or at least 99% of your notebooks, should be launched under 30 seconds. The second is notebook launch success rate. What this means is that at least 99% of your notebook launches should successfully transition from initialization state all the way from running state. So let's look at a dashboard. Now, this dashboard basically shows success rate across various time periods. So we measure it every hour, every day, every 7 days, and every 28 days. Now, the success rate itself is defined as the number of good events over the number of bad events. The burn rate is defined as the errors observed in a time window over the error budget for that particular time window. And the error budget itself is 100% minus the SLO. So if your SLO is 99%, you basically have an error budget of 1%. And that's going to give you the margin of creating new features, trying out new experiments on your platform. Although, if you have a high burn rate, that should actually trigger new alerts for triaging. And that's something we do. And if you're interested, I would encourage you to watch this talk by my colleagues Alexa and Ankita on Dashboards and Dragons, crafting SLOs to tame the AI platform chaos, And this was from KubeCon Europe 2025. So do check it out. All right, so let's look at some examples of how SLOs and SLAs actually help us. So in the first case, we were noticing a pattern where the pod initialization SLA was going down. So what that meant was usually that users were able to launch their notebooks, let's say, under 30 seconds. And now it was taking more than 1 or 2 minutes. And what we noticed was that this was isolated to only notebooks with a certain pip package. So we installed a tracker on our cluster, which tracks what's the fetch time from pip for a certain pip package. And we found that PyTorch is a very heavy package and takes a lot of time to fetch from pip. And that was delaying the startup. So one of the mitigation strategies for us was to pre-bake PyTorch into the Jupyter image itself. And this increased our SLA requirements. In the second case, we have notebook launch success rate. And that was going down significantly. In parallel, because we have a validation framework that integrates with Jupyter API and Argo, we were noticing some increased GPU error rates. So correlating these two events helped us isolate that particular incident, and we worked on the GPUs to fix them. Now, once we fixed the GPU issues, we saw that the success rate improved. So in this way, defining SLOs and SLAs gives you a one-shot view of the health of your platform. All right, so to summarize, Jupyter Notebooks can be launched and scheduled using Argo Workflows. The Jupyter API supports notebook creation, kernel control, and code execution. And it is essential to define SLOs and SLAs to measure reliability targets. Continuous monitoring and observability maintain your system's health and allow you to make safe upgrades. And finally, and most importantly, reliability itself is a core platform feature.